guys, now that we have gone through the basic things on set theory, we are at a point that where we can start up with probability, right? The theoretic probability. And as an introduction to probability, first we see what probability deals with. Probability deals with, or it applies to random experiment, right? So this probability theory, it applies to random experiment, not just any experiment. The experiment has to be a random experiment. So what is randomness, right? Randomness means you cannot predict things, unpredictability. Randomness has an inherent property of unpredictability. It's random. So what are random experiments? Let's see what the definition of random experiment is. Right. So what is a random experiment? A random experiment is an experiment, not just any experiment, it's an experiment that can be repeated. So you should be able to repeat this experiment. Suppose I do this experiment in Sri Lanka, another person in China can do the same experiment, right? Repeatedly, right? Can be repeated and has well-defined outcomes. It should have well-defined outcomes. Very important. These two things are very important. It should be an experiment that could be repeated and has well-defined outcomes. What are examples? The basic examples: tossing a coin. Tossing a coin. Right? Can you repeat this? Obviously, you can repeat this experiment. Nowadays we are watching T20 cricket match. So it starts with a coin toss. It can be repeated, this experiment. And it has well-defined outputs. What are the well-defined outputs? Heads or tails. If you flip it once or if you toss it once, you get heads or tails. Those are the two well-defined outcomes, nothing else. Another one, rolling a six-sided die, right? Rolling a six-sided die. Rolling a six-sided die. This experiment can also be repeated, and it has well-defined outcomes. What are the well-defined outcomes of a die? When you roll it, you can get either the face values, right? So if it is a six-sided die, you can get 1, 2, 3, 4, 5 and 6. Those are the well-defined outcome. You cannot get 7, you cannot get 10 unless it's there. Six-sided die, this should be, right? Or picking, pick a card from a standard deck of cards, right? Pick a card from a standard deck of cards. So there are 52 cards in a standard deck of cards. You can pick a card from that. You can pick 2 cards or 3 cards or any number of cards. You can repeat this experiment and it has well-defined outcomes. So when you pick a card, it should be one of the 52 cards, right? Not anything else. It should be one of the 52 cards. So the outcomes, if you pick only once, the outcomes would be 52 cards. Okay, so that's what is meant by a random experiment. So I have written the outcomes here. You can get either heads or tails. Here 1 or 2 or 3 or 5 or 4 or 5 or 6, right? With outcomes. And if you pick a card from a standard deck of cards, the outcomes would be ace of hearts, or ace of clubs, ace of diamond, ace of spades, then 2 of spades, 3 of spades, the list goes on, right? 52 cards. Okay, right. Next definition, sample space. What is a sample space? Now this is why we learned sets in the first video. Sample space is actually a collection or a set of all possible outcomes of a random experiment. So here also we deal with random experiments. Sample space is not just an outcome all possible outcomes of any experiments, Sample space under in probability is defined as set of all possible outcomes of the random experiment, right? Okay, so since this is a set, we have to use set notation, and to represent the sample space, we sometimes use omega, this symbol omega, or capital S, right? Let's do some examples, right? Tossing a coin once, right? So what is the sample space in this case? Say omega, or let me use S instead. S. Since it is set, we have to represent the outcomes within curly brackets. You can have heads or tails, right? Heads or tails. These are the possible outcomes when you flip it once. Tossing a coin once. All possible outcomes. B. Rolling a dice. Roll a dice once. Six-sided. Roll a six-sided die. Six-sided. Otherwise, that statement is vague. Six-sided dice. Sample space in this case, can you guess what is the sample space? That should be the O. That should represent all the possible outcomes of this random experiment. So if it is six-sided die, mark from 1 to 6, so you can get 1. You roll it, there's a possibility that you can get 1. Right? O, 2, O, 3, O, 4, 5, 6. That's it. You can never get 7, 8, or anything else, right? So these are the possible outcomes. Right. Right. So there are three ways of representing sample space. This is one way, listing out all the possible outcomes as a set. It is given as a set. What are the other two methods? Yeah, let's use the same method. Tossing a coin once, or we can use, let's say B, tossing a coin twice, right? Sample space would be, you can represent it like this. You can get first head, or heads, tails, heads, or tails. These are the all possible outcomes. When you flip a coin twice, on the first trial you can get head, on the second trial you can get tails, right? So this represents the first trial, this is second trial. So when you write it like this, the first one represents the first trial, second one represents the second trial. Or you can use a space diagram. The second method is to use a space diagram, sample space diagram. Let me show you that. Okay. We can represent the same thing. First toss, second toss. Right. So on the first toss, you can get either heads or tails. Second toss also you can get heads or tails. Right. So this coordinate point, this point refers HH. Right. First time you get heads, second time you also get heads. This represents this point, first tail, second heads. This point, first tail, second tail. This point, first head, second tail. This is a sample space diagram, right? Sample space diagram. The third method is to use a Venn diagram. So we learned about Venn diagrams in video 1, so I'm not gonna specify that here. Right, so this is called a sample space diagram. Right. So you can use either one of these methods. Either you can use this one or this one. Right. Sometimes we use tree diagrams as well. So using tree diagrams is also another way of showing the sample space of a random experiment. Next definition is for event. What is an event? We learned this in the first video. Event is actually something that will occur, something that might occur. right? Occurrence of something. That is the simplest definition of an event. But mathematically, under probability, it is given a definition, so you have to learn this. It is a subset of sample space. Now, once the sample space is defined, you can make subset from other sample space. So, any subset is called an event. Right? A single outcomes are also events. So, remember from the power sets in the first video, we can make up so for this one, actually there are 4 subsets, right? Since we have two outcomes in the sample space, then 2 raised to 2 would be the number of subsets that you can do here. So what are the events? You can get null event. This is one event or one subset, or you can just get heads. Right? So you can ask, what is the probability of head appearing if you toss a coin once? Tails is also an event, right? Then this whole thing, ST, this is also a subset. These are all the subsets. So these can be events for this. Right? Another example would be roller dice, roller 6-sided dice. Then what should be the sample space? In this case, 1, 2, 3, 4, 5, 6. Right. So now based on this, we can come up with subsets. Right. For example, let's say event A. Event is also a set. So you know that we use capital letters to represent set. Event A. This could be just one. A single outcome, right? Single outcome. We call them simple events. Actually, we call them simple events. A simple event is a single outcome of a random experiment, right? Just one outcome of a random experiment. That is called a simple event. Right? Or another outcome, another event. We could define it as like this: 1, 2, and 5. This is another event, right? Because this is a subset of this. Right? We can define another event. Even numbers. Let's say C set is even numbers. Right? Even numbers. In that case, C would be 2, 4, and 6. Right? Let's define another set. Say numbers less than or equal to 4. In that case, this event D, has these outcomes. Less than or equal to 4, then it should be 1, 2, 3, and 4. Right. Then after defining the event, we can ask, what is the probability of this event happening? What is the probability of A event happening? B event, right? So for this one, you have 2 to the power of 6. That means 64. 64 subsets. You can build up 64 subsets or 64 events from this sample space. So that's a huge number. I'm not gonna do all of them. Right. So the next definitions are simple event and compound event. Simple events and compound events. So these are all events, right? So event is actually a subset of the sample space. Now those subsets can also be categorized into 2 parts: simple events and compound events. So what is a simple event? Simple event actually is a single outcome of a sample space. Just one element, or we can say an element of the sample space, right? So that is easy. An element of a sample space. This definition is easy to understand. An element. So you can list out the sample space of a random experiment. Then just one element is called a simple event, because you cannot break it down anymore. Compound events is an event consists of 2 or more simple events. For example, Let's say roll a dice. This is a six-sided die. From here onwards, if I say roll a dice, it usually means six-sided dice. If it is not, I will specify. Then this is the sample space. Right. So simple events. What are the simple events? These are simple events. 1 is a simple event. That is an element of sample space. 2 is a simple event. 3 is a simple event. 4 is a simple event. 5 is a simple event. And 6 is a simple event. So there are 6 simple events. What are compound events? Compound event means it can be 2 or more simple events. For example, 1 and 2. Right? It consists of the simple event 1 and also simple event 2. Or we can have 1 and 6. Right? Or we can have just 1, 2, 3 and 4. Right? These are compound events. Right? Compound events. Right. The next definition is null event. So you learned this already. Null event is an event with no outcome. Right? It's an event with no outcome. Nothing will happen. So this is simple we use. Now our objective is to determine the probability of certain events. Now can you guess the event of this happening? Right? If you do a random experiment, if you do an experiment, one of these outcomes must come. Right? One of these outcome is possible. Right? So suppose you toss a coin, either heads or tails must be there, must appear. Right? Either one of these. Right? So there is no chance of getting, nothing will happen. Right? Nothing will happen. That means null event will not be there if you do an experiment. So the probability of getting a null event would always be 0. So we can definitely say one of these outcomes should happen. Right? There's no chance of not happening at least one of these outcomes. So this is what it means, null event. And examples for a null event would be an integer between 9 and 10. So there is no integer between 9 and 10. That's one example. Or the numbers that are both odd and even. Can you find a number that is both an odd and even number? No, there is no such number that is both odd and even. Right. But if you say even numbers and a number that is both even and a prime number, yes, there is just one number, that is 2. 2 is both prime and 2 is also even number. Right. So that is not a null event in that case. Right. The next one is mutually exclusive events. Mutually exclusive events. Right. So what are mutually exclusive events? If two events are mutually exclusive, it means if one event occurred, the other one cannot occur. If the other one occurred, the first one cannot occur. Right. Those events are called mutually exclusive events. In other words, mutually exclusive, if there are two mutually exclusive events, that means both events cannot occur at the same time. Right? So that's another definition. Events that cannot occur at the same time called mutually exclusive events. Right? At the same time occurrence means an overlap, intersection, common thing. Right? So therefore, A intersection B, if A intersection B is a null event, then we say A and B are mutually exclusive events. Null means, you can see that from the Venn diagrams, intersection means null means A and B are separated. They are separated. So there is no common elements that represent both A and B, which means A and B cannot occur at the same time. Okay. Mutually exclusive events. Right. So in probability, when you convert this notation into probability, then P, probability of A intersection B equals 0. Please keep this in mind, we will get to this later. If the probability, this means probability of A and B happening at the same time is 0. In that case, A and B are mutually exclusive events. හරිද? ඉතින් මේක හැම වෙලාවෙම වෙන්නේ නැහැ. මෙහෙම වුණොත් මේකේ value එක 0 නම් A and B are mutually exclusive events. If PA intersection B is non-zero, මේක 0 වෙන්නේ නැත්නම් A and B are not mutually exclusive. They are not mutually exclusive. Please learn that. Then make a para වෙන්න බෑ. So what are examples? Examples being when you flip a coin once, you can either get heads or tails. You cannot get both, right? So heads and tail are mutually exclusive events. Examples: toss a coin once, right? Getting heads and tails are heads and tails in this case are mutually exclusive events. So I use ME. ME means mutually exclusive. This is shorthand notation. If you toss a coin once, you can either get head or you will get tails. Those are the only possible outcomes if you toss it once. You cannot get both at the same time. So both will never happen at the same times. Those events are called mutually exclusive events. Another example would be if you toss a die, then you can get 1, 2, 3, 4, 5 or 6. These outcomes. You cannot get 1 and 2 at the same time. You cannot get 1 and 6 at the same time. You cannot get 1, 2, 3, 4 and 5 at the same time. There's only one possibility, one of the 6 outcomes, always, right? You cannot get 2 outcomes at the same time if you toss only once, right? So those are mutually exclusive events. Right. The next definition is exhaustive events. So we need these definitions. Exhaustive events. What are exhaustive events? So exhaustive events are events such that their union will represent the sample space. So when you combine all them, when you take the union of these exhaustive events, then you get the sample space. Those are called exhaustive events, right? So let's do a graphical intuition, then you will understand what it means. So this is the Venn diagram, right? In the Venn diagram, you can have A, B like this, A, B, right? But you have elements outside as well, right? Outside. So this is, let's call this a sample space. Oh no, just this one. Oh, let's just call it S, right? Just to show you what it means. Okay. In this case, A and B. Now, you know that A and B are not mutually exclusive because there's an interaction between A and B. Now, are they exhaustive? Are they exhaustive? A and B. If they're exhaustive, then their union must represent the sample space. What about the union here? This is the union. Right? So, if we take the union, then it will not represent the sample space because there can be elements outside, right? So these elements will not belong to either A or B. Therefore, A and B are not exhaustive. They do not represent the sample space. So in this case, A union B is not equal to the sample space, right? So you can say this is a subset of the sample space. If that is the case, A and B are not exhaustive events. Right. So what about this case? Example A, example B. You have a Venn diagram. Now in this case, Venn diagram is divided into 3 parts. Right. Let's call this A and this B, right? And there's another region like this. This region is C. Okay. So there is interaction between A and C, then B and C. B and C, this would be the interaction. Between A and C, this would be interaction. But if you take the union of all three, union of all three means everything. Right. If you take the union of all three, then A union B union C. Union C, in this case, this is equal to the sample space. Right. So when you take the union, it represents actually the sample space. Therefore, A, B and C are exhaustive events. They are exhaustive events. But if you just pick A and B only, then A and B they are not exhaustive events. Right? It has to be all three, because the union of all three sets gives you the sample space. Right? If you take only A and B, the union between A and B will not represent the sample space. Or A and C, they will not represent the sample space. So if you take just A and C, union between A and C, then it represents this region, this part, but this part is missing. So I believe that you get a clear idea about this. Right. This is graphical intuition. Okay. Now let's do an experiment. Example, another example. Toss a coin once. Right. So what is the sample space in this case? Heads or tails. Right. Heads or tails. In this case, heads and tails are exhaustive events. Right? Heads and tails. These two events and tails. Because when you take the union between these two, union with T, this is equal to H and T. This is a union. Right? When you take the union between two sets, you know that you have to put all elements in just one set, right? Without repeating anything. Right? Okay, exhaustive events. Another example would be roll a dice. Right? In that case, let me just use omega. 1, 2, 3, 4, 5 and 6. These are the possible outcomes. Then 1, 2, 3, 4, 5, 6 combined are exhaustive events. When you combine all of them, then they are exhaustive events. So 1, 2, 3, 4, 5 and 6. All 6 events combined are exhaustive events. Exhaustive events. Right. Now, there's another thing to note. If there are exhaustive events, that means one of the events must occur, definitely occur. One of them must occur. When you consider all of them, they are exhaustive events. But if you just pick one or two, let's say event 1 and just event 2, if you consider only 2 events in this case are not exhaustive. They are not exhaustive. Okay. So for events to be exhaustive, when you take the union of all of them, it should represent the sample space. Otherwise, they are not exhaustive events. Right. So one thing to note here. So we learned about mutually exclusive events. We learned about exhaustive events. So there's another thing called mutually exclusive and exhaustive. Mutually exclusive and exhaustive, which means these events must satisfy exclusive part and exhaustive parts. Exclusive parts means there are no interaction. Intersection should be none. Right? Suppose A, B and C are events of S. Right? Then if A intersection B is null, that means no interaction between A and B. B intersection is null, no interaction between B and C. A intersection C is null, no interaction between A and C. And A union B union C represent the sample space, right? So this means mutual exclusiveness. This means exhaustiveness. So then A, B and C are mutually exclusive and exhaustive events. For example, if you take a Venn diagram, right? This is the sample space. Suppose we have three events like this. This is A, this is B and this is C. You can see that there is no interaction between A and C. It's a fine line between A and C. No intersection. A and B, no intersection. B and C, no intersection. But if you combine all these three, if you take the union, then it will equal to the sample space. So this is these three events are mutually exclusive and exhaustive events. Right. The next one is equally probable events. Equally probable events, just as the name suggests, these events have equal chances of occurring. The probability of these events are the same. Right? They have the same probability. Events that have equal chances of happening. Examples, tossing a fair coin. Fair. Right? Fair coin can එක පැත්තකටවත් bias නැහැ. If you toss a fair coin, there's the two events, heads and tails, are equally probable events. They are equally probable events. So chance of getting heads is equal to the chance of getting tails. 50% chance of getting heads, 50% chance of getting tails. Tossing a biased coin, right? Biased coin. Biased mean biased, let's say biased towards heads. That means if you toss a coin many number of times, you might see heads appearing, right? Most of the time heads will appear if it is biased towards heads. If it is biased towards tails, when you record all the tossing, then you would find that the tails will appear many times, right? Tails will appear many times if it is biased towards heads. So in that case, chance of getting heads is not equal to chance of getting tails, right? So biased coin, when just tossing a biased coin, this case not equally probable, right? Not equally probable. In this case, equally probable. In this case, equally probable. Right. Right. Then the last definition, event space. Event space is a set that contains all possible events of a given sample space. All possible events. So we learned a set like this in the first video. We call it a power set, right? So this is analogous to a power set. ඔක්කොම subsets ටික sets වල ඔක්කොම subsets ටිකට අපි කියන power set එකක් කියලා. Probability වල power set එක equivalent වෙනවා event space එකට. Same meaning. And මෙතනදී why do we use two different words here? Because sets they don't worry about random experiments. A set can be a random experiment or can be something else. But in probability, we deal with random experiments only. So we have to come up with different word set, right? Different word set. So that's why we use event space. Okay. Right. So that's the end of all the definitions that you need to learn. Then maybe in the next video during the class session we will learn about probability, how to calculate probability given a sample space, right? So there are three definitions basically. The first definition is the classical definition, then you have the experimental definition, and then you have the axiomatic definition. So we will learn these theories later on. Thank you for